Okay, so we are about to start the second talk of the morning. We have Florent Balacheff, who is going to speak about free curvature generalization of hyperbolic identities. So please.
Thank you very much for the introduction and for the invitation and the organization of this nice conference. It's a pleasure to be here. So I will talk about the following question: how to generalize hyperbolic identities, and by identities I mean equalities or inequalities, to the free curvature setting. That is, so hyperbolic identities are like equalities or inequalities which are valid for any hyperbolic metric on some topological manifold. And we would like to generalize this result, these formulas, to general Riemannian metrics without any curvature assumption. So it will be clear with my introduction what is the objective. So let's start with two examples of such generalizations. So the first one is a well-known formula. So we have a closed orientable surface of genus, so we will suppose that the genus is bigger than or equal to 2, such that there exists some hyperbolic metric on it. So here by hyperbolic metric, I mean a metric of constant curvature, sectional curvature, equal to -1. Okay, so if you have this object, then you have a well-known formula, which is that the area is constant. So this is an identity, an hyperbolic identity, and equal to 4 pi times the genus -1. Okay, so this is a basic example of hyperbolic identity. This is true for any hyperbolic metric that you can put on your closed surface sigma. Okay, so how to get a free curvature generalization of this identity? So you have a first way to do it, which is well known, which is the Gauss-Bonnet formula. And which says that the following quantity, so you have minus the integral over your surface of the sectional curvature times the area from, for the Riemannian metric, is constant, equal to 4 pi the genus -1, as is all for any Riemannian metric on your surface. Okay, so here we get a free curvature generalization of this hyperbolic identity using here a local or infinitesimally metric invariant. Okay, so this generalization is well known. There is another theorem which can be interpreted as a generalization of this identity. So this is maybe I'm sure that the theorem everybody knows, but that this can be interpreted as a generalization of this identity. Maybe this is not so well known. So you have a Katok inequality which says that for any Riemannian metric that you put on sigma, then the following is true. So you take an invariant, which is the volume entropy. I will define it in a few seconds. Time the area is always bigger than or equal to 4 pi times the genus -1. Okay, and you have equality with equality if and only if the metric G is some multiple of a hyperbolic metric. Okay, so here there is a new object that appears in the conference, which is the volume entropy. So as this is the first time I will define it. So this is an asymptotic invariant, which is constructed as follows. So you take the universal cover of your closed surface on the weight with the corresponding Riemannian matrix. Okay? Universal cover. Then you fix any point here. Let's say it's x tilde, and take any radius r and look at the area of this ball. Right? So this ball will behave in most cases as in the hyperbolic case, which means that it will have an exponential growth with positive factor. And then the factor that appears is exactly this volume entropy. So you will have this. So you take the log of the volume of the area for the Riemannian metric J tilde of this ball. You take the log, you divide it by r, and you let go this quantity, r to infinity. And, well, there is several facts that are well known. So this quantity exists, this limit exists always, does not depend on the chosen point. So this is why I can define it like this. It's called the volume entropy. So why this is called entropy? So the definition volume is clear from the definition because you have volume here. Entropy because this is a lower bound of the topological entropy of the geodesic flow. And you have indeed equality when the curvature is non-positive. Okay. Sorry?
What is K?
K. It's R. It's my R. Sorry. Better? Sorry. So in fact, this means that this is equivalent to say that the area of my ball of radius r in the universal cover behave more or less like the exponential of the entropy times r. Okay? So this is this factor that appears when you are writing the area like this. Okay. So you have this beautiful inequality, which holds for any Riemannian matrix. And why this is a generalization of these hyperbolic identities. So if J0, G dot is hyperbolic, if J is hyperbolic, then, well, the volume entropy is constant equal to 1, okay? And as you have equality when this is any multiple of the hyperbolic matrix, then you recover that the area is equal to 4 pi, the genus minus 1. Okay, so it's like a way of viewing this theorem, maybe in some sense artificial, but it will be really productive as you will see later. Okay. Here we can observe that this quantity is invariant when we multiply the metric by any factor, so by rescaling the metric, because the entropy behave like the inverse of a length. Okay, and also we see that in this generalization we have equality here, equality there, but here we have a generalization with an inequality. Okay. So for this talk, this is not a problem to generalize things like this. Okay. So this was my first example. The second one I would like to explain today is the systolic inequality. So for a hyperbolic metric, then you know, surely you know that the systole is bounded by the genus like this. Okay, so we can write it like this is roughly 2 times log of the genus. Okay. And in fact, this upper bound is roughly optimal, meaning that there exist examples of surfaces with hyperbolic metrics whose systole is bigger than some constant times the log of the genus. Okay? So I will not explain all the, any example, but I mean, this is optimal in this sense. So what are the three curvature generalizations of this? So one is, the systolic inequality for surfaces. So here I will write things like this. You take any Riemannian metric on sigma, your surface. Then you have that the systole is bounded by something. So you will find 2 times log of the genus. And you have here to multiply by the square roots of the area of your metric divided by 4 pi gamma minus 1. Okay? So, of course, when the metric is hyperbolic, the area is equal to this factor, and then you recover this upper bound. Okay? So this result is due to Katz and Saburo. In 2005. So let's just mention that Gromov finds that the systole was bounded by the log of the genus with some constant here, which was not as optimal as this one previously in his feeding paper. Okay. In the proof of Katz and Saburo of this systolic inequality, they prove a nice, yeah?
For a given genus, for a given variable genus.
For?
For a given variable genus, is this sharp?
No, we don't know. No, we don't know sharp surfaces for systolic inequalities, which are hyperbolic. We don't know. There is some partial result when the metric is negatively curved, and this is by Stefan Saburo. But in the general case, when you allow any curvature to appear, you don't know. Okay, so Katz and Saburo prove something which is interesting, and it's connecting to the second viewpoints, to the second way that we can generalize this systolic inequality. And it says that the product, so recall that the volume entropy, I say this is, it has the dimension of the inverse of a length, okay? The systole is a length, so the product is invariant. And you can bound it by 4 times log 32 times the area over the square of the systole, okay? If J is systolic extremal. So I mean by that you take a metric which is almost optimal for the systolic ratio, the systolic volume. And then for this type of metric, you have this bound, that the entropy times the systole is bounded by this function. So here you can see that there is an interesting product that appears, which is this one. Okay? And you have this systole here, then you can produce a quantity which is invariant by rescaling the metric, multiplying by the entropy. So this is natural to ask if you can bound, always bound this product entropy times the systole. And the answer is yes for surfaces. So you have the following theorem. So this is the second generalization. This is entropy versus systole. Okay. And it says that, like always, for any Riemannian metric on your surface, then the volume entropy times the systole is bounded by some constant that depends only on the genus. Okay? So this is a result by Saburo, Stéphane Saburo, in 2006. Okay? Well, this is not exactly a generalization of this inequality, because when you have a hyperbolic metric, then the volume entropy is equal to 1, and you only get that the systole is bounded by some universal constant, but it is in the spirit of, we are doing this thing like roughly, so this is like a generalization, okay? It is expected that, so this constant is a bad constant. Sorry, Stéphane. Well, I mean, it's nice to have a constant, but it's a bad one. And the optimal one should be something like C log times gamma. It's expected to be something like this, and to recover this systolic upper bound in the hyperbolic case, okay? In fact, we have a similar inequality, which is true for graphs, with a constant which is this one, okay? That I prove in around the same time. So it is likely that the optimal constant should be of order log of the genus. Okay. No, it's a constant that depends on the, a constant that, constant depending on the genus. If it has been the constant times the genus, it will be, it will have been a good constant. No, I don't remember. It's like exponential, the genus, or something like this. You don't remember, okay. Okay, so maybe to be complete for this introduction, so this is the end of my introduction. Here we have, so this theorem generalizes to higher dimensions. This is the Besson-Courtois-Gallo theorem on volume entropy, and it implies Monster rigidity theorem, so this is a really nice results. This one can be generalized also for essential manifolds, and in the case of hyperbolic manifolds, so meaning closed manifold which admits a hyperbolic metric, then you have a statement which is similar to this one, proved by Gromov, okay? And finally, for this example, it does not generalize to higher dimensions. So you can prove that for any manifold M of dimension more than 3, then you can find a sequence of metrics such that its product goes up to infinity. Okay. What is the conclusion? Yeah.
How does the volume entropy scale supermetric? Is this product scale invariant?
Yeah. The volume entropy is like 1 over a length. Okay, so if you multiply the metric by some scaling factor, it will multiply by the inverse of it, and the systole by this factor. Okay, so the conclusion is the following. To get curvature free curvature. generalizations of hyperbolic identities. So I mean identities or inequalities, of course, use the volume entropy. Okay. So of course this was not the initial idea that that we had in mind with my co-authors, because we were just with Louis Merlin trying to understand what was the relation between the volume entropy and the length of a base of homotopy base of loops in some manifold, but well, in fact, using what we have done, we get that this philosophy was true to some extent. Okay, so now I will show you another inequality, hyperbolic inequality that can generalize to the free curvature case, just using the volume entropy. So this is called the log 2k minus 1 theorem. Okay, so this is a theorem by Anderson, Canary, Keller, and Shallen in '96. And it says the following. Okay, so if gamma is a free Kleinian group, so I will explain what is it in a few minutes. Kleinian group generated by key elements A1 to A key, then for any x still in the hyperbolic space of dimension 3, then you have that the following sum is less than or equal to 1 over half. Okay, and function here is 1 over 1 plus exponential the distance of x tilde ai x tilde. Okay, so I will explain now all the words in this theorem. So what is a Kleinian group? This is a discrete subgroup of the isometry of H3 which preserve the orientation. Okay. And then what do I mean by a free Kleinian group generated by A1 A key? Here there is some things to precise. So this is a subgroup, Kleinian subgroup, generated by this key element and isomorphic to the free group with key generators. Okay? So you have no relations between the element A1 to Ek. Okay? So what does this theorem say? It says that so you sorry. So you have the hyperbolic space, H3, that is represented by a three-dimensional ball. And then you have here some point in it. And then you have A1 acting on this point and create a displacement, which is A1 x tilde. And then you measure the distance with respect to the hyperbolic metric. And you have this strange relation. Okay, so for instance, here you have E2, so E2 x tilde. And in the other direction, you will have the inverse of A2 times x tilde, A1 minus 1 x tilde. And you create like this something which is like a tree. This is the traduction of the fact that the group is free. Okay? What you will observe here, drawing this picture, is a tree of order 2 key. Okay? So this theorem says that if all these displacements, if all these displacements are short, there should appear a relation. Okay? So this is called the log 2k minus 1 theorem because it says that there is at least one index, I dot, such that the displacement by the corresponding element of the Kleinian group is bigger than or equal to log 2k minus 1. Okay? So at least one displacement should be large enough. Okay, so this is what say geometrically this theorem. I'm moving too much, maybe, for the television. Okay. So, okay, you have this nice theorem. And you can say, okay, how can I generalize this to any any Riemannian metric? So here we will interpret that the quotient by H3 by gamma is a manifold, and then okay, you can take any Riemannian metric on it, then go back to the universal cover, and can you say something? Well, this is like a distance, like a length, so you can try to multiply by something which looks like the volume entropy, okay? And we get the following theorem that we prove with Louis Merlin. And it says the following. So you get, if you have a manifold M tilde, which is a complete manifold, which is simply connected, and you take on it any Riemannian metric. So this is the first part. Then you take also a discrete subgroup gamma, discrete subgroup of isometries of these manifolds, such that, well, gamma is generated by key elements. So this time maybe, no, I call it also A1 to A key. And such that this is a free group of order key. Okay, so you have this assumption. Then you will have the following theorem. So the following sum. So this is 1 over 1 plus exponential the something associated to the group gamma and related to the metric G tilde. So the delta of gamma tilde, maybe I put the gamma, the G tilde inside, times the distance of x tilde times a high x tilde. So this sum will be less than or equal to 1 over half for any point in your manifold. Okay, so you have something which looks like a free curvature generalization of this result. Any dimension. Any dimension. Okay, so here is a new object, which will be like the volume entropy when the quotient by of M tilde by the group is indeed a closed manifold. Okay, and this invariant is defined as follows. This is the critical exponent of the group. And this is defined as the following limit. Sorry, one number. So it looks like the volume entropy. So here you are taking one point, and you look to all the element gamma whose displacement of this point is less than or equal to R. Okay, this is called the critical exponent because there is associated to this subgroup a series, and this is the critical value for which you have convergence or divergence of this series. Okay, so let's mention that it was already known for pinched negative matrix, already known when the metric was bounded like this. Okay, by a result by who? And okay, so if gamma is a Kleinian group, what happens? So you can see that all these conditions are realized here as a special case. But what happens is that in general, we have this invariant, which is less than or equal to 2 if the manifold is H3 with the hyperbolic metric. Okay? So you don't strictly recover this theorem as a special case of this one. But, so this is on the dark side. On the bright side, you have that there exist subgroup gamma, Kleinian groups, such that the critical exponent is strictly less than 1. Okay, so in that case, this inequality improves this one. Okay, so you have this generalization, and the way to generalize this inequality is just multiply any metric invariance that appear by the correct power of the volume entropy or of the generalization. So what happens if the manifold empty J tilde and is the universal cover of some Riemannian manifold, and you take gamma as the fundamental group of your manifolds? So you have the following corollary. So if Mg is a closed Riemannian manifold with non-trivial fundamental group, and let fix key bigger than or equal to 2, of course, then if you have loops C1 to Ck, so there are loops based at the same point, and such that the subgroup of the fundamental group generated by this point, by these loops, is a free group of order key. Okay, so we say that the loops are freely are homotopically independent. They have no relation in the fundamental groups. Then you will have that the sum from E. Okay. So you take here 1 plus the exponential of the volume entropy of your manifold times the length of these loops, C high, and this is bounded by 1/2. Okay, so it sounds like a systolic inequality. This is not strictly speaking a systolic inequality, but it looks like a universal bound for some curves involving some Riemannian invariant. This time this is not the area, but the volume entropy. Okay. So this inequality is quite interesting for for a reason, is that you can see that if you are trying to modify the metric, the Riemannian metric, such that the length of the shortest slopes goes to 0, okay, then this quantity has to go to 1, and this will be 1/2. So you will have that any other loops, which is homotopically independent from the loops that you are contracting, goes to infinity. Okay, and this is a generalization of a consequence of the Collar lemma. Okay, if you have for hyperbolic metric on the surface, you can choose like you want the length of the closed geodesic of some family, and if you have the length which is going to 0, then you can find an annulus whose width is large, and there is a clear function between the width here and the length of the curve. But in particular, it means that any curves intersecting this loop and being that way freely independent, homotopically independent, which have its length going to infinity. So this result generalizes in some way this consequence of the Collar lemma. Okay. So this is the first example. So of course, what we did with Louis Merlin is we are trying to understand this type of theorem. So this theorem come out, and then we discover that it was, in some sense, a generalization of this one. And then working a little bit, we found this generalization. Okay, so let's be enthusiastic. So if you have any favorite hyperbolic identities, what would it be? So there is a celebrated hyperbolic identity, which is called McShane identity. So let's see what says McShane identity. It says the following. So you have a hyperbolic torus with one point removed. Okay, so punctured hyperbolic torus. And if you take any punctured hyperbolic torus, then you will have the following identity due to McShane. So you take the sum over the simple closed geodesic, leaving on your punctured hyperbolic torus. You take 1 over 1 plus exponential of the length of this closed geodesic, which is minimal in its own homotopical class. And then you have that this is equal to 1/2. Okay, so this is a beautiful inequality, which was generalized by Mirzakhani and used to compute the Wade-Peterson volume of the modular space of hyperbolic metrics. Okay, so what we would like to try to do is multiply by the entropy and see if this is also true for Riemannian metrics. But unfortunately, so far, I have no clue to generalize it to the free curvature case. Okay. But in the bright side, we can generalize another famous hyperbolic identity, which is due to Basmadjian. So the identity by Basmadjian is valid for any dimension, but I will just state the identity in the case of dimension 2. So you will have a compact hyperbolic surface, let's say sigma G dot, such that the boundary is geodesic. Okay, we can start with this object. Then you have on it what is called orthogeodesics. So there are geodesics going from the boundary to the boundary, and minimal in its own relative homotopy class, which means that they will be geodesic and orthogonal to the boundary. Okay, and we can produce with that what is called the orthospectra, which is just the collection of lengths of these orthogeodesics. Okay, orthospectra. This is the sequence of lengths of the orthogeodesics to the orthogonal, minimal geodesics orthogonal to the boundary. Okay, and then you can describe fully the length of the boundary of your surface for the hyperbolic metric, and you have that this is equal to a function which is the following. So you take factor 2 times the sum over so maybe here I have to put G dot to be correct, G dot, and then you have some function which is log of the cotangent hyperbolic of L over 2. Okay, so what is interesting here is that the length of the boundary can be completely described by the orthospectra. So if two compact hyperbolic surfaces have the same orthospectra, then they should have the same length of the boundary. Okay. Okay. Here, this function you can rearrange to be equal to 1 plus 2 times 1 plus exponential of the length. So you can see that there is some parallel with this type of function. I don't know exactly the connection between both, but there is obviously something that appears here. Okay. And you will, we will try to generalize it to get something which is always true for any Riemannian matrix. So here you have a length, so we will try to multiply this by some entropy, and here you have also length, so we will try to multiply here also by entropy, by volume entropy, and indeed it works in this case, and we get the following theorem. So the theorem is the following. If G is a Riemannian metric on a compact surface sigma such that the boundary of sigma is a closed geodesic, then the following holds true. So you have that the length of the boundary, which is bigger than or equal to, so the equality transforms into an inequality. So you have 2 times. Here you have some entropy, but I will explain in a few minutes what is this is sigma prime, okay, times, so you have here arcsinch, and the sum, as always, over the orthospectra. Okay, 1 over 1 plus exponential of this entropy times the length of the curves which are here. Okay. So there is some kind of generalization which is obtained by multiplying the length which appears in this Passmann identity by some entropy. Okay, so what is sigma prime? So you have sigma, which has as boundary a unique closed geodesic, and then you can do only, you do the reflection, okay, and now you get a closed surface, and this is your sigma prime J prime. Okay. Okay, so you get the generalization. Of course, we don't think that this lower bound that we obtain is sharp, but there is a lower bound, which was not obvious. I mean, okay. And now I will present a third result, which can be obtained with this philosophy. So maybe here I can say something more about this. Okay, this theorem. You have so we don't know how to generalize it to the free curvature case, but we have a result which is comparable to this. Not really comparable, but with the same flavor. And this is the following: is that so this is a result by myself and Louis Merlin. Maybe I say this is a proposition. So if you have a metric graph, gamma, which looks like the following one. So you take a point and you take loops of length L1 to L key. So this is a bouquet of circles of length L1 to L key. Maybe I take not gamma but G. Okay. So if you have this metric graph, then you will have the following. That's the sum of this functional. So you multiply the length Li by the volume entropy of the metric graph G times the length of the curves. This is constant, and this is equal to 1/2. Okay. So we prove this using a result by lim, which allows to calculate the volume entropy of metric graphs. Okay. And in fact, this is how we prove the generalization of the log 2k minus 1 theorem is using this type of graphs. Okay, so you see that there is, in all these theorems, there is something which is comparable, but I mean, for Max chain identity, I have no idea how to prove this. Okay. So let me finish by presenting a third example of generalization of these hyperbolic identities that we can do. And I will speak about spines of manifolds. Okay. So we take M will be a closed connected manifold. And we suppose that the fundamental group is not 0. Okay. Then we will define the spine, a spine of a manifold M will be a subcomplex. This is a finite complex. Here we will suppose always that the dimension is less than the dimension of the manifold. Okay. So this is a spine. If you can collapse the manifold M, from which you have removed an open ball. So if this collapses topologically to S. So what does it mean? It means that you have your manifold, you take a needle, and you punch, you make a puncture on your manifold, and then it's like a balloon, it goes flat. And what remains from this operation of decreasing the dimension is your spine. Okay. So maybe a few examples of this notion to understand what is it. So for instance, if you have the sphere Sn, well, a point is a spine. Okay. And maybe if we focus on S2, and then you take any graphs, it will be a spine. Okay. In the case of the torus, two-dimensional torus, then the following graph is a spine. And more generally, if you take any point P and a Riemannian metric on your manifold, then the cut locus will be a spine. Okay. So this is like the kernel of the topology of your manifold. So this notion, the spine is related to the notion of complexity of three-dimension manifolds. And we have the following. If the dimension of M is bigger than or equal to 3, then you have that the P1 of the spine is isomorphic to the P1 of the manifold. Okay? And if the dimension of M is equal to 2, you only have a surjection on your fundamental group. Okay? So here, for the two torus, the spine has this graph. And of course, the fundamental group here is the free group with two generators, and this is not Z2. Okay, so you can try to do some systolic geometry and define the spine systole. Okay, so we define the spine systole to be so the infimum over the spine of the area of the spine. So by area, I mean the codimension 1 Hausdorff measure. Okay, so there exists a result by Martelli, Novogoda, Pluda, Rida, which says that when the manifold is a closed surface, then this infimum is a minimum, and it is realized by a combination of some geodesic graphs. And in dimension 3, there is a nice theorem which ensures that this infimum is also a minimum, a result by Chow, which was a student of Michael Friedman. Okay. So here is a result of hyperbolic geometry. So this is Johan Porti who proved this theorem in about 10 years ago. And it says that if you have a hyperbolic metric G dot on a closed orientable surface of genus gamma, then the spine systole has length, because this is a codimension 1 finite complex. When the dimension of the manifold is 2, this is a graph. The length of S for this metric is bigger than or equal to 3 times 2 times the genus minus 1 times constant depending on the genus, and this constant, you have an explicit description of it, and it goes to log 3 when gamma is going to infinity. Okay? So you have this sort of hyperbolic inequalities, which is true for any hyperbolic metric you take on your surface. And in fact, this is optimal. You can produce a hyperbolic metric whose spine systole will be equal to this quantity. Okay? So when I explain all these results to Johan Porti, he asked myself about what if we can get a generalization of this result for higher dimensions. And so I will finish with two theorems, which say that indeed you can generalize it. So the first is like a proposition, because this is like a simple combination of already known results, which says that if J is a Riemannian metric on the orientable closed surface of genus gamma, then you have that the volume entropy time the spine systole, so I will write min of this quantity, okay, is bigger than or equal to 3 times 2 gamma minus 2 log 2. Okay. So we are not so far from Porti's result. And another result which I obtained with Wolfgang Pitsch will say that the same is true for almost no, but a large family of hyperbolic manifolds. Okay, so if M3 G0 G dot is a closed hyperbolic manifold, and we have some restriction such that the fundamental group is not virtually two generated, then you have something which looks like this result, which says that, so this is for any Riemannian metric here. Then you have the product of the volume entropy of your manifold times the spine systole, which is bigger than, so here you have to take square roots because this is like an area, and this is bigger than some constant, which is the following. Okay, so you get the generalization of this inequality hyperbolic identity in the free curvature case. And okay, so we have this strange condition on the fundamental group because in fact what we did with Wolfgang Pitsch was to get such kind of inequality, but for two complexes which are two free, meaning that any the fundamental group has the following property: if you take any two elements in the groups, then the group generated by these two elements is free. Okay, and that's it. Thank you very much.